third video in a series discussing the applications of moment generating functions. In today's video, we are going to focus on how moment generating functions can tell us interesting properties about the sums of independent random variables. So, without further ado, let us introduce a property. So, let x1, x2, xn be a series of random variables with moment generating functions, or with MGFs. We'll call it mx1 of t, mx2 of t, and mxn of t. And we're going to define S1, or S, just S, is equal to x1 plus x2 plus plus x to the n. Or in shorthand notation, we write the sum of I equals 1 to n of xi. Here is my claim. My claim is that if x1, x2, xn, and so on and so forth are independent, then the moment generating function of S is actually, which again would be defined as the expected value of t to the s, is equal to the product of all the functions, of all the moment generating functions of x. This is going to be my claim. And in fact, this claim that I make here is going to be able to, we're going to be able to use this to potentially determine the distribution of sums of random variables. So let's prove this fact using our definition of moment generating functions. So here's sort of a mini proof of this. So let's start with ms of t. Well, the moment generating function of s is again by definition e to the ts. In this particular instance, we can rewrite this as e to the t, and I'm going to write in brackets x1 plus x2 plus plus xn. Yeah. Then, of course, we can distribute the t within inside the brackets. So doing that, we'd get the expected value of tx1 plus tx2 plus plus txn. Now, here's an interesting point about exponential distribution, or the exponential function, I should say. The exponential function, recall that if you have e to the m plus n, that is the equivalent of saying e to the m times e to the n. So by virtue of this property of exponentials, well, I should say powers in general, we can rewrite this expression as a product of terms. And that product of terms becomes e to the tx1 times e to the tx2 times ... should probably put times rather than dots, e to the txn at the end. Now, x1, x2, x3, and x4 and whatnot and I'm going to rewrite it in this funny notation. This, by the way, symbolizes independence. Xi is independent of xj, where I is not equal to j. In other words, as we said before, x1, x2, they're all independent from one another. When the index is different, they're independent. What this means in general is that if you have two, let's say x is independent from y in general, then it means that if you take the expectation of a function of x times, say, a function of y, then that gives us the expected value of the function of x times the expected value of the function of y. That is an important property of independent random variables. And because of that important property here, when we're taking the expected value of a series of functions of independent random variables, we can actually rewrite this as e to the tx1 times the expected value of e to the tx2 times ... times e to the expected value of e to the txn. And by definition, we know what each of these represent. Hey, what do you know? This represents the moment generating function of x1 at t times this is the moment generating function of x2 at t times ... times the moment generating function of xn at t. And finally here, if we go back to our original property, we said it was the product of moment generating functions. And exactly that's what this represents, the product of the moment generating functions. So that's all good and well. Let's see how this could be used in practice through a series of very important examples about common distributions. And I'll write them out now. The first example considers the Bernoulli distribution. And here's our question. Suppose that xi, our random variables, they all have a Bernoulli distribution with parameter p. And let's say there are n of them for I equals 1. And let's say they are a sequence of, I should say, independent random variables. We're asked to find the moment generating function of S. And in particular, we're going to try and find the distribution of S from that moment generating function. So, here we go. Let's have a look. Well, we're going to use the property that we had above, which was that, recall, the moment generating function of the sum is the product of the moment generating functions. So, firstly, actually, let's find the moment generating function. So if x has a Bernoulli distribution with parameter p, that tells us that the moment generating function of each xi is the following. That tells us it's equal to 1 minus p plus p e to the t. By definition of some of the other videos that we've done, we're going to derive that, of course, but for now, take this fact as given. But you can see other videos of how it's derived. Here, that means that the moment generating function of S, which we said was the product of I equals 1 to n of all the individual moment generating functions, that has to be the product of I equals 1 to n of 1 minus p plus p e to the t. Now you'll notice that here the index is I, but there is no variable here that depends on I. So in other words, the index, I should say. And so in other words, we're just multiplying this by itself n times. This leaves us with 1 minus p plus p e to the t to the power of n. And actually, this is a recognizable MGF. This is the MGF of a binomial distribution. And we know by the uniqueness of MGFs, S has to be a binomial distribution, because only a binomial distribution has this MGF. Let's have a look at a second example. In this example, xi is going to be a binomial distribution with parameters mi, so they each of these xi's has its own unique number of trials, but all have the same parameter p. And that's again going to be for n independent random variables. Find the distribution of the sum, which I should say is equal to x1 plus x2 plus dot 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 plus xn. Again, we're going to use the property that the moment generating function of a sum of independent random variables is the product of each of their respective moment generating functions. Now, we know that xi, if it's simulated a binomial distribution, say with parameters MIP, then this implies that the moment generating function of the ith random variable is equal to 1 minus p plus p e to the t to the power of mi. And this is a known moment generating function. You can look at other videos to see how this one is particularly derived, but for now we're going to take it as given. This means, of course, that the ms of t, which is equal to the product, is going to be the product of I equals 1 to n of 1 minus p plus p e to the t, all to the power of mi. Now, there's an interesting thing here about this product and how to evaluate this product, or simplify it, I should say. In general, if you have, say, a to the power of n times a to the power of m, then we can rewrite this as a to the power of m plus n. And in general, if you have a look here, what we're multiplying is, we're multiplying a, you can think of this as your a, and we're multiplying them and we're taking a different power each time. And therefore, the resultant e to the t expression becomes m1 plus m2 plus dot 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 plus mn, I should say, mn. Or in a simplified manner, e to the t to the power of the sum of I equals 1 to n of mi, as a little bit of a more formal notation. From here, we're actually going to recognize that this as well looks like a moment generating function of a binomial random variable. Here is your element that depends on p, But here, if it was all together, this represents the total number of trials. So in this particular instance, we'd have that by uniqueness of MGFs, S is distributed as a binomial distribution with parameters the sum of all the individual trials plus or with parameter p. In other words, the sum of binomial random variables with the same probability of success p is also a binomial random variable, except this time you sum across all the trials or all the independent trials. Let's take a look at a third example. In this example, we're going to look at a geometric random variable which has a probability of success parameter p. So let them be, again, I equals 1 to n, so n random variables, each with the same parameter p. They're independent, and we want to find the sum of a geometric random, or the distribution of a geometric sum of geometric random variables. So the first thing to note is if xi, or if each of your xi's are geometric, so if xi is a geometric distribution with parameter p, then this actually tells you that the moment generating function of xi is defined in the following way: p e to the t on 1 minus 1 minus p e to the t, and of course that's true for t less than or equal to negative ln of 1 minus p. So this again is a known moment generating function. I encourage you to look at some other videos on the channel, if they're already up, on how to derive this particular expression. But for now, we're going to take it as given. So again, to find the moment generating function of S, we're going to find that, I'm going to say that's the product of I equals 1 to n of the individual moment generating functions, which in this case is the product of I equals 1 to n of p e to the t 1 minus 1 minus p e to the t in the brackets, which in this case, remember again, in a similar way, the p e to the t and 1 minus p to the t, they're all independent of the index, so effectively we're just multiplying the same number over and over by itself n times. That means in this product we can rewrite this as p e to the t 1 minus p e to the t, and then all to the power of n. And in fact, this is also a recognizable moment generating function. This particular moment generating function is by definition the moment generating function of a negative binomial distribution. So again, by uniqueness of MGFs, S must have a negative binomial distribution with parameters given by n and p. In other words, the sum of geometric random variables, of independent, identically distributed geometric random variables, I should say, is a negative binomial distribution, which sort of makes sense because individually, a geometric random variable represents the number of trials before the first success, and a negative binomial distribution represents the number of trials before the nth success. So by summing each of the individual times that the number of trials that it takes to get to the first one, plus the number of trials that it takes to get to the second one, plus all the way to the number of trials that it takes to get to the nth success, that gives you a negative binomial in some sense. Now let's take a look at a fourth example. In this example, we're actually going to have a series of negative binomial random variables, each of them with the number of successes required to be R. And of course, they're all going to have the same probability P, but the number of successes that are required by each is different from the next, Ri, hence why we've got the subscript Ri to denote that distinction for each xi. So in this case, if this is true, then the moment generating function of a negative binomial distribution is the following. It's given by p e to the t on 1 minus 1 minus p e to the t all over, I believe it is to the power of Ri. Notice here, it's to the power of Ri because that is our value here. And this is only defined, actually, I should specify, for t less than negative ln1 minus p. So from here, we can calculate the moment generating function of the sum. That, by definition, we know is the product of I equals 1 to n of the individual moment generating functions. We can put those moment generating functions into the formula, so that becomes p e to the t 1 minus 1 minus p e to the t all to the power of Ri. And in a similar vein to before, recall when we said we had if we have a to the power of n times a to the power of m is equal to a to the power of n plus m. Again, in this particular expression, we're multiplying a series of powers, each with the same base, but a different power. And so then this product can become p e to the t 1 minus 1 minus p e to the t to the power of r1 plus r2 plus dot 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 plus rn. And of course, in a shorthand form notation, that becomes p e to t 1 minus 1 minus p e to the t all over itself to the power of the sum of I equals 1 to n of Ri. And we can also recognize this particular function as the PL, a moment generating function of a negative binomial distribution. It just has different parameters. It has the parameters p and it has the parameter sum of I equals 1 to n of Ri's. So again, by the uniqueness of MGFs, it tells us that S must have a negative binomial distribution, negative binomial, and the parameters are going to be the sum of I equals 1 to n of Ri and P. And in some sense, this also makes a logical sense, because if you think about each of those random variables individually, this is the one of them, xi, is the total number of trials required to get Ri successes, or sorry, the total number of failures required before we achieve Ri successes. And so if you were to add them all together, that is the equivalent of saying you need Ri, but then you need another Ri, or you need R1, but then you need R2, then you need another R3 successes, and so on and so forth. You need a whole lot of successes to finally stop your random variable. And by that definition, it is, of course, as well a negative binomial random variable. So, now we've had a look at that, let's have a look at another example. So in this example, I've shortened the description a little bit so that I can write it in a more succinct fashion. This is saying that xi is independent, sorry, I should say not IID, but independently distributed, or they're independent from one another, and they have the each parameter has a parameter lambda I, and that's true for I equals 1, 2, 3, 4, 5, 6, 7, all the way to 9 and to n. We're going to try and find the distribution of the sum. So without further ado, let's continue, or let's go ahead. So we know that if xi has a Poisson distribution with parameter lambda I, then this tells you that the moment generating function of xi is equal to e to the lambda I e to the t minus 1. And again, this particular expression, or this moment generating function, is a known moment generating function of a Poisson distribution. Please see other videos to see how this is particularly derived, but for now we're going to take it as given. Again, the moment generating function of the sum, which in this particular instance is defined as the product of all the moment generating functions because they're independent, is equal to the product of I equals 1 to n of e to the lambda I e to the t minus 1. And in this case, note that when you're taking the product of terms with the same base, in other words, in general, when you've got a to the n times a to the m, that gives you a to the n plus m. So these terms all have the same base of e, and we're multiplying those terms together. That is the equivalent, therefore, of saying e to the power of sum all the terms, I equals 1 to n of lambda I e to the t minus 1. Or perhaps in a bit easier shorthand for now, we can rewrite this as lambda 1 e to the t minus 1 plus lambda 2 e to the t minus 1 plus dot 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 plus lambda n e to the t minus 1. Now, all of these particular instances, or all these particular sums here, have a common factor of e to the t minus 1. So I'm going to factor that out in the power. So if I do factor the e to the t minus 1 out as a factor, I'm left with lambda 1 plus lambda 2 plus dot 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 plus lambda n. Or if I wanted to rewrite this in a nice succinct way, I could rewrite this as the sum of I equals 1 to n of lambda I times e to the t minus 1. And what do you know? This also looks very similar to the MGF of a Poisson distribution, except instead of just a single lambda in the expression, we've now got the sum of lambdas in the expression. And so therefore, by uniqueness of MGFs, the sum has a Poisson distribution, with in this case the parameter is the sum of all the rate parameters of the individual Poisson random variables. And that's a very interesting fact. The sum of Poissons is a Poisson. Let's look at another interesting example. In this example, we're going to look at the exponential function. And we're going to say that each xi has an exponential distribution. All of them have lambda. So they each have lambda as their respective point of interest. And what we want to know is the distribution of the sum of those random variables. Now, in order to do this, we know that if xi is an exponential distribution with parameter lambda, then this tells us that the moment generating function of xi is lambda on lambda minus t, and it is defined for t less than lambda. Again, I encourage you to look at a video of how this is derived, but for now we're going to treat it as given. So in this particular instance, this gives us the following. The moment generating function of s, which again, because they're independent, is going to be the product of I equals 1 to n of the individual moment generating functions, which in this case is the product of I equals 1 to n of lambda on lambda minus t. Now, again, the I or the index here, no term in the index is dependent. Also, no term within the sum here, also the product, is actually dependent on the index, and therefore we're technically just multiplying this same number a total of n times with itself. So this becomes lambda on lambda minus t to the power of n. And of course, this is still for the case where t is less than lambda. That condition still must hold. Now, we actually recognize this distribution, or the moment generating function of this particular distribution too. This is the moment generating function of a gamma distribution. And by the uniqueness of MGFs, S must follow a gamma random variable with this time parameter n and lambda. And it follows from this that the sum of exponentials is a gamma distribution. Let's have a look at one more example. In this example, we're going to concern ourselves with a gamma random variable, where each of the gamma random variables are independent, but they each have the same rate parameter, but they have a different shape parameter, alpha I. So in order to do this, we need to first find the moment generating function of xi. So the moment generating function of xi, it's a gamma random variable, has the following look about it is lambda on lambda minus t to the power of alpha I. Again, alpha I is different for each of the xi's, and that's for t less than lambda. It follows that the moment generating function of the sum is, again, because they're independent, it's going to be the product of the moment generating functions of xi. We substitute in our moment generating functions I equals 1 to n, lambda on lambda minus t to the power of alpha I. And again, in a similar point to before, when you have a to the n times a to the m, that's the equivalent of a to the n plus m. In this particular instance, we're multiplying a series of terms together, each with the same base but a different power. And so this can simply be rewritten as lambda on lambda minus t to the power of alpha 1 plus alpha 2 plus dot 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 plus alpha n. And if we want to write this in some shorthand notation, it's lambda minus t all to the power of the sum of I equals 1 to n of alpha I. And what do you know? Again, this also looks like a gamma distribution. It's a gamma distribution with now a parameter, not alpha I, but rather the sum of alpha i's as our shape. And still we have the rate parameter as lambda. And so then this tells us that by uniqueness of MGS, S has a gamma distribution with sum of I equals 1 to n of alpha I lambda. Let's go through one last important and perhaps a very important example, one of the more famous examples of this particular property. This example, we're going to look at a normal random variable where each of the xi's has its own unique mean and has its own unique variance. What does the sum of a series of independent normal distributions look like? Well, without further ado, let's have a look. Firstly, the distribution of xi, or the moment generating function of xi, is equal to, in this particular example, it's the exp of mu t plus a half sigma squared t squared. This is the general expression for the moment generating function of a normal random variable with parameter mu and parameter sigma squared. But in this case, remember, we're not dealing with just mu, we're dealing with mu I. It's different for each parameter. So we write mu I sigma squared I. From here, we can now find the distribution or the moment generating function first of the sum, which we know they're independent. So I is equal to 1 to n of the moment generating functions of the normals, which in this case is the product of I equals 1 to n of exp. In fact, I won't write exp. I'm going to rewrite it as e to the power of mu I t plus a half sigma I squared t squared. That's just substituting in what we had above, just rewriting it as e to the power of as opposed to exponential of the term. From here, again, we're going to note that when you take the product of a series of powers, each with the same base, one of the important rules is that a to the power of n times a to the power of m is equal to a to the power of m plus n. And in the same way here, we've got a series of terms. The first term is e to the mu 1t plus a half sigma 1 squared t squared times e to the mu t plus a half sigma 2 squared t squared times dot 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 times all the way to e to the mu n t plus a half sigma n squared t squared here. And by the property here that we described before, where if they all have the same power or base, we can simply add the powers. That's what we're going to do. We're going to have e to the mu 1t plus a half sigma 1 squared t squared. We can then add the second set of powers here, which is our plus mu 2t plus a half sigma 2 squared t squared plus dot dot dot, and then we're going to go all the way to mu nt plus a half sigma n squared t squared right at the end. And from here, we get another interesting property. And that interesting property is the fact that we can collect like terms. So you see, we have a t here, we have a t here, we have a t here. We can collect all those together. In fact, we can factor out the t, and this leaves us e to the t mu 1 plus mu 2 plus dot 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 plus mu n. That's if we concentrate ourselves on these particular terms. Similarly, we can actually take a common factor of a half t squared, a half t squared, and a half t squared in the second, for the second terms of this sequence. And so we can take out a half t squared, and then if we factor that out, we're left with sigma 1 squared, sigma 2 squared, sigma n squared, which gives us sigma 1 squared plus dot dot dot, plus sigma 2 squared plus dot 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 plus sigma n squared. Or if we wanted to rewrite it in a much nicer notation or simpler notation, we could rewrite this as I equals 1 to n of mu I, the sum of mu i's times t, plus a half the sum of I equals 1 to n of the sigma I squareds t squareds. And now what do you recognize under this expression is that this awfully looks like the same moment generating function that we presented before, except instead of mu I, we have the sum of mu i's, and instead of sigma I, we have the sum of sigma i's in the expression. But all else equal, it's the same. What does this tell you? it's a normal distribution too. And so this property together means by the uniqueness of MGFs, the sum has to also have a normal distribution, and it has the parameters the sum of I equals 1 to n of mu I as the mean, and it has the sum of sigma I squared from I equals 1 to n as the variance. So altogether, this is the new variance. So you can, yeah. And there you have it, one of the most important properties that you will see that appears a lot in probability and statistics. The sum of normals is also a normal. And in fact, the sum of normals is normal where you take the sum of their means as the new mean and the sum of their variances as the new variance. We've gone through a lot of really important examples here, gone through a lot of important proofs, in fact, realistically, of how to show that the sums of particular random variables give another distribution of a well-known random variable. We've been using MGS to do that. I hope this video was informative. I hope to see you in the next one.